Hello, everyone. Thank you for joining our session today. I'll be introducing Jorge Alarcon, who's the Global Technical Manager, OCM at Bureau Veritas. He'll be giving his insight on lessons from 5 years feeding a neural system with oil analysis data. Jorge, I leave you with the floor.
Thank you very much, Arturo. Thank you for this time. Thank you, Wojciech. You're always there. So, what I'm going to tell you in the next minutes is just a process that I've been dealing with for the last couple of years, almost 7 years when I started this journey. It's basically trying to let my experience on trying to feed an algorithm system with the oil analysis information that I was providing to the system. So it was a journey. I learned a lot of things. I learned how to do things. I learned especially how not to do some other things. So data analysis is undoubtedly one of the frontiers, not only for us people that are working in the predictive maintenance, but also for many different sectors like the bank, food suppliers and stuff like that. So everyone is looking for that part of the information in the data that it's providing maybe more understanding of how the business is going or how the things are going or how the things should be done. So we are aware of this situation. A lot of people have been doing a beautiful stuff related with data analytics and also with some other projects related with this. So a typical industrial machine will have probably between 2 to 12, 20 samples in a year, no more than that. In a perfect scenario, a machine will have, let's say, around 100 samples during its entire life. And this volume of samples is too small to feed a system, this type of systems, of course, artificial intelligence system, to get some information from it. So basically, with this amount of, with this volume of information, and spreadsheet will be more than enough to run any basic calculation, statistic analysis, or anything like that. The good thing is that labs they have that we have a lot of thousands, in some cases millions of samples from similar machines, and also that are with similar lubricants. So this makes the lab a lake of information where we can pull a lot of information. We can learn a lot, and of course we can share part of that information that we have learned through the years. So um, in this case, we were talking about not only going from the basics, starting with, let's say, probability, statistics, and going higher in this chain, but also going to apply what we'll say the latest technology, artificial intelligence, machine learning, algorithms, and in my case, feeding a neural network with this information. But let's talk about initially about algorithms because all these nice and beautiful tools are based on algorithms. So algorithmy is a Latin version of a name of a mathematical genius, Persian genius. His name is Mohammed Musa al-Khawaziri. I don't know if I pronounced it correctly or not. Sorry about that. Who introduced the Hindu-Arabic numerical system to the West. So new concepts like algebra, for example, were very innovative, and it was introduced by these mathematical genius. So what happened through the time was in the medieval Latin, algorithmus simply mean a decimal number system. By 13th, 14th century, depending on the source, it had become an English word, but it wasn't until 19th century that algorithm came to mean process, right? So algorithm is a process, is a set of step-by-step rules to solve a problem, right? So very basic thing. But nothing changed until probably until 20th century in around 1942, 1943, when Alan Turing, the father of the modern computer science, worked in a theory that any machine will, if it follows different rules or instructions, it will be able to solve these complex or a lot of different complex mathematical problems. So from this perspective is what we have many different algorithms. So the first algorithms, if we go back to history, probably were when two numbers were multiplying, and we were talking about 2,000 years before our area. And we can jump from there for many different algorithms that still these days we're using this algorithm. So some of them are mainly using, for example, in bank industry. Some of them are using to detect languages, speeches. So a lot of different functions of these algorithms, very old algorithms, right? But we are using it these days. So if we go back to 2004, for example, Google search said that that was the highest peak when somebody, or a lot of people were looking for the word algorithm. So around 12,000 searches per day in 2004. And from that point, the search for algorithm was reduced. Now, these days, only 50%, like 6,000 searches per day, occur in Google for a word, for algorithm as a word. Right. So I'm not sure what happened. All right. So let's go back to the lab world, right? So the lab receive, I don't know, a couple of thousand samples in a day. Unfortunately, some of those samples are not exactly from the same machine, right? So we can receive sample A, for example, in month one. We will not receive another sample from component A until 12 months gone, right? So after a year, probably we'll receive a sample. So the problem for us, for the people that are working in these analysis, data analytic thing, is that we can plot what's happening with component A until we have a new sample of component A in 12 months. But a lot of things can happen in 12 months, right? So the thing is, applying these beautiful rules and beautiful algorithms, what we can do is trying to connect the dots. So basically, we can try to understand what's happening with component A and how component A is going to be at some point here, for example, not only based on the analysis of month one on component A, but also applying the other analysis from different components. So this is probably the most complicated part of these project, of these type of analysis, because we have to allow the neural network to fill in the gaps, basically. So the RNA will have to say, all right, so component A maybe will be here in 6 months, or component A will be here maybe in 7 months. So that's the well, the algorithms and all these equations and numbers come in, right? Because the initial part, of course, is the basic of oil analysis. So that is the baseline of it. But we need something, and in this case, the algorithms, to try to plot the rest of the information because we don't have that information. So from the model perspective, we have an input, and as input, we are talking about the different tests that are developed in the lab, in any oil analysis lab. Viscosity, acid number, FTIR, so name it. You have it there. That's an input, right? That's an input. So those inputs need to be plugged in into what we call a recurrent cell. So a recurrent cell basically is it's a node when where the function will do this thing. So we're telling basically in this node that the input needs to be applied in a formula basically. So besides that, it's very important to provide a weight to the different inputs, right? Because the weight will be the decision, will be part of the decision when we are applying this equation here. So the problem in this case is that my criteria can be very different as logic criteria, for example. He will say that for him, acid number is the most important thing, and he will apply a weight of 0.9. And for me, I will say that based on my experience, I will apply a zero point 0.1, right? So this is probably one of the most critical parts of the analysis. And this is where a lot of the analysis fail because the decision weights are critical, and these are based on our experience or based on someone else's experience. So after we have that, the nodes can create a cycle. So it basically means that every time that we have an output, if we have a low coefficient or a coefficient that is not enough for our results, the result will go back and it will try to look for a different decision weight. So the inputs will vary again. We'll have a different input based on weight, and we will have to run the equation again until we have a high coefficient, or we will be pleased with the result, with the output based on the coefficient that we are having. That's what the neural network will do. Of course, in this case, we are not talking about just one node. We are talking about many different nodes, and because the oil analysis is based on chemistry and physical chemical analysis, these nodes can be as much as 54. Like in one of the cases that I've been working with, I was able to identify 50 different for nodes, right? So 54 is a lot. It's very complex to deal with that. In some cases, an analysis on about 20 different nodes will take more than 88 hours. And this is supervised neural network. We're not talking about unsupervised thing. So it takes a lot of time, right? It takes a lot of time. So what are the limitations of these method? Because it is beautiful, it's nice, we have nice results. Initially, the result was not what I was expecting for, but after some time, I found this couple of things that are the limitation of the method. So a high degree of knowledge related with oil analysis is needed. So depending on the expertise of a person, the weights, as I said before, may vary. If the weights vary in the function, we'll have a different output, right? So basically, we can manipulate the system based on what we are expecting to have, and that is a problem because we are manipulating something and we are looking for some type of output that will come after we manipulate the system. So many of the unfinished projects are due to these facts because we are manipulating. We're not allowing the neural network to do this thing, right? To work based on the information provided. The assignment of weights is probably the most critical part of this thing. It's probably the most important one and is one of the most difficult part to play with. Because again, we are assigning the weights based on our expertise. So, for example, in one case, I got assisted by another a person who has a different type of knowledge on oil analysis. So this guy has more knowledge in engine oil analysis than me. I'm focused more in the industrial part. So his approach was completely different than the one that I have. So taking a look at the weight on the network, so their weights were completely different than the ones that I have been using. So again, this is one of the critical limitations for the method. So what are the outputs or what are the outcomes after running a lot of different analysis? So for example, if we talk about grease bearing analysis, I was able to identify in a couple of locations five different type of clusters, they say. So these are basically how the bearings are behaving, right? So for example, here these two are what I call the bathtub type of behavior because initially we can have this type of information, and at some point at the top of this part we will have a critical part of the analysis where probably will the bearing will suffer from a potential failure here, functional failure. We're not talking about critical failure, just functional failure. So I was able to identify different models, right? So different models that can tell how the bearing in this case is behaving. So based on the models, we can expect or we can predict what's going to happen next. Maybe the good thing is if you tell this information to a planner, to a maintenance planner, probably he will say, all right, when we get to this point, probably we'll need to get some bearings to replace the ones that are ready to fail, right? So these are good models that I was able to pull out from these analysis. Another conclusion or another good thing that I was able to have from these type of analysis is that I found that again with the same thing models, right, aging models. So I found that probably component A in a month, X month, will have the most likely model to apply. So in this case, this component has 27% of likeliness to be fit into these model, and maybe more, like in 70%, like in this case, to be applied to this type of model, to this type of in-service model. So the bearing, basically what I'm saying here is the bearing is behaving like this more than this, right? And of course, we're not talking about just one sample here. We're talking about at least a couple of samples from this unit, but those samples are applied to a lake of information, right? So that's the criteria that I use to plot this sample into one of these models. So it fits better in this one than this one. Another good thing that I found here is that clustering is a beautiful and amazing tool. After running a different analysis on different units, like in this case gearboxes, I was able to identify that the clusters here, in this case, like we have four different clusters: orange, yellow, blue. So these clusters are telling us basically how the processes are behaving. So probably we can say again that unit H5, for example, It's and at some point it will be ended here. So this is this one, trying to apply the results into a model. This one is more type of grouping different units, trying to understand what's happening with all of them from a specific perspective. And of course, we humans like to predict the future. We are really bad predicting the future. That's for sure. But in this case, for example, what I was able to find again is that I was able to identify a time range and with the risk evaluation. So basically, component E again, it will behave in these four different options based on the time range. For example, there's a 7% chance that that component E will have a higher risk of problem based on the functional failure, of course, in about, I don't know, 72 months, 52 months, around this range, right? So these are the options that component E will have. And of course, again, we will look for the higher option in this case. Like in this case, 37% is probably the most likely option for this component based on the analysis run by the system, right? So there's no only one benefit of working with this type of methods, with this new things that we call AA or artificial intelligence and neural networks or stuff like that. So we can have, and I'm pretty sure that a lot of people that have been working with these tools are having many different outcomes, right? So the benefits for this is probably something that we didn't see enough yet. So we are at the beginning of understanding and getting the benefits of these things. Like in this case, I was with a 5-year analysis. I was able to get at least 3 different dimensions to understand how the bearing is behaving, and of course, or the gearbox, and of course, this entire analysis is based on the results provided by the lab, oil analysis lab, right? So this is the basic thing. This is where the information is pulled from. And we don't have to forget that as the critical part of this information is based on quality. So we have to have quality results, right, from the lab. We're not talking about the data analytics right now, so just about the lab. So a good lab with quality results, it's probably the most important thing in this case. So apply to OCM, these type of tools will allow to method data visualization where all layers are immediately identified. So this is the first thing, right? So I have these all layers based on this information. Something wrong with the unit, or I can say that something's going to be wrong in the next couple of months, years, probably. Second thing that I found running this humans have problem predicting the future, right? We are really bad doing that. We don't know what's going to happen tomorrow, but we like to say, try to say what's going to happen tomorrow. So these tools are providing an alternative. I'm not saying that this is the tool that'll let us know what's going to happen with that bearing, what's going to happen with that gearbox. No, just an alternative, the different type of outcomes. So like any other method, there's a limitation here. And the main limitation from my point of view is the knowledge on OCM, the knowledge related on the oil analysis results. That's critical for any method like this or running a calculation, basic calculation, that is critical. And one of the main problems is the lack of information. Unfortunately, labs they don't have enough information, right? So we just receive a sample, and we probably will know nothing else about the sample, the type of machine, type of lubricant, the hours of that machine, the hours of that lubricant. So that part of the information is as critical as the sample received in the lab. So if you are an end user, and you are looking for these type of solutions, you have to provide the entire universe of the information. Just don't submit a sample with this information. You will waste your time. And for for people who are working in this, you have to have two different expertise, right? You have to have the oil analysis expertise, and you will have to have the data analytics experts in your team to try to succeed in this, because this is just a new approach. So data is the most important thing. I don't know how many years ago somebody said data is the oil of the future. So in this case, I think data is the most critical, the most important part of this entire picture. All right, I think we have time for questions.
Jorge, great presentation. Thank you very much.
Thank
We
you,
have
Alfredo.
6 minutes for some Q&A. I think we have one question from Ahmed Bashir. His question is, what is the success rate of this application?
All right, good question. So, in a couple of cases, I apply this information trying to, I would say, predict the future, right? So, I have a customer, and I said to the customer, I think these gearbox, based on the analysis, is going to fail, functional failure. It's going to fail in the next, I don't remember exactly, couple of months, right? So I was very close in probably 4 occasions of 7. So I missed 2 for some reason, of course, but I was very close for the other 5. I don't know, so 80% probably. That's the rate, but this is just the beginning, right? I mean, I've learned from the last 5 years a lot, but I don't have the results that I was expecting for yet. I just finished this thing, right? So now I'm trying to fit information, and I'm pretty sure I'm going to have more, not success rates, but probably I'll be able in the next years to say this is not working, right? So let's look for something else, right?
Great, great. Let's see if we have any more questions.
Perfect. It's lunchtime.
Yeah. Anyone else have any questions for Jorge? Uh, I also encourage everyone to connect with Jorge. If you do have a question you would like to send him privately, that'd be the best way to do it. Yeah.
Yep. All right. Thank you, everyone, for your time. Wojciech, my friend, over
Perfect.
there.
Thank you. Thank you very much, Jorge.
Thank you. Have a good one. Have a nice weekend.
You too. Thank you very much, everyone, for attending. And like I said, please connect with Jorge if you have any additional questions, and we'll leave you go. Thank you very much, and it's been an excellent presentation. Thank you.
Thank you.
All right.